Hello guys, this is the last portion of the topic on fasteners. So we deal with a very common connection, which is the eccentric shear connection, used on used on steel brackets and corbel. So in the eccentric shear connections, there are two methods used for the analysis. Uh, and the first one is actually the traditional elastic analysis, which is also known as the vector analysis, while the second one is the more rational one, which is an ultimate strength analysis, or what you call the plastic analysis. And for reasons of practicality, the latter will be discussed in this section. So let's consider now a fastener group or a bolt group attached to the steel bracket as shown in the figure. So we have 6 bolts uh, acted upon by a force P, which is arbitrarily oriented. So the location of the bolts, of course, are known. That's why the centroid, or the center of gravity, is readily determined by simply taking note of the center of the bolt location. For this particular analysis, the load P, which is of course eccentrically loaded and arbitrarily oriented, will cause the fasteners or the bolts to translate and rotate at the same time, simultaneously about the center of gravity CG. And if we are to consider deformations to be within the elastic range, uh, we have to deal with both the translational displacement and the rotational uh, uh, displacement to come up with the total displacement of the whole system. However, the complication of dealing with this may be reduced to a pure rotational effect only by identifying a point of rotation known as the instantaneous center of rotation, okay, which is somewhere uh, here at this point. So if we refer all rotations exactly at the instantaneous center of rotation, then our problem on both translation and rotation will simply be reduced to a rotational or a moment problem. So the requirements for static equilibrium then must be satisfied by, of course, the three static equation on forces horizontal, forces vertical, and moment about the instantaneous center. And take note that if we consider a general equation in the form of a summations series of the effect of the resistance Ri with that of the single load P, we will come up with this simpler equation in this form. So all horizontal component will be a function of the cosine of the angle. If we consider this as your sample fastener to represent uh, the I index for this resistance, therefore your angle to be considered in that regard will be theta I. Okay, so in all situations, your RIs will be in general reckoned from the angle theta I, and that angle is actually referred to the horizontal direction. So all horizontal component will be in terms of cosine, okay, while that of the vertical component will be cosines, okay, or vice versa. I think there's an error here. Okay, so this is Ri. We are taking the component of Ri with respect to the angle. Sorry, if this is your horizontal reference, your theta here will be reckoned from the vertical. Okay, that's why the horizontal component, which is this one, is a sine function. Okay, a sine function of the angle theta I, and the vertical component will be a cosine function of the angle theta I. For the P value or the load, if the load is referred to the vertical axis here by an angle delta, then the perpendicular distance between the center of gravity up to the line of action of your applied load will be reckoned from the horizontal, such that your horizontal component again will be a sine of the angle delta, and your vertical component will be the cosine of the angle delta. The sign are negative because this is going downward to the right, and the sign of these are all uh, positive because they are directed upward and to the left. So in that case, the moment about the instantaneous center can now be solved by simply multiplying all the components of Ri's and P with that of the moment arm. So for the Ri, the perpendicular distance between the angle, sorry, the resistance with that of the instantaneous center is simply the shortest distance from the location of the bolt going to the instantaneous center defined by your di's, while that of P has to be computed or analyzed using some geometrical uh, computation, such that if we consider now the total perpendicular distance coming from this point to this point. Okay, so we can actually extend this line. So this is equivalent to E. And then if we continue extending this line here, we can come up with the total. Okay, so this must be parallel or perpendicular, or sorry, parallel to this line here and perpendicular to this line here. Okay, so we need to compute for this small distance from the center of gravity up to this point. Okay, so while noting that your XO and YOs are the reference distances from the center of gravity to the instantaneous center, we take note that if we look into this triangle formed and project, okay, this distance here, okay, so our target is to determine now this total distance to be added to the value of E to complete your moment arm for P. Okay, so taking note that this is XO distance, and this is this total distance here, vertical distance here is simply a YO distance. Okay, so if we're going to extend this value here, so this is a YO distance. Okay, so what is now this distance here? So take into consideration this line which is parallel to this line. So we can solve for this small distance here, and if we add it to this distance here, which is actually the same line, okay, that makes this distance, okay, we will come up with the total distance here to add up to the value of E in this figure. Okay, so let's look at the angle. If this is your angle delta, then this angle here must also be a delta angle. Okay, so if we know XO, this small part here, the green from here to here, let's say this is point O, and this is point P. Okay, so the distance OP will simply be equal to XO, the cosine of delta. Okay, so what remains is this distance from OP to M. Okay, so the distance PM, which is also equal to this distance here. PM there is equal to P prime M prime. Okay, such that this triangle now, which constitute your YO, okay, will have an angle delta here. Okay, so this angle is also delta. So if I want to get this is a sine. Okay, so M prime or M prime P prime is simply equal to the distance YO multiplied by the sine of the angle delta. So to add up to the total moment arm from this point to this point, so this moment arm from the P up to here, which is perpendicular, will simply be equal to E plus XO cosine of delta plus YO the sine of delta. Okay, so the load P will cause the fasteners to translate and rotate simultaneously about the center of gravity instead we deal with the instantaneous center of rotation for us to be considering only rotational uh, deformations or displacement rather than a combination of translational displacement and rotational displacement. So in this regard, your moment arm that I'm talking about earlier is now derived in this form, which is the same as that value here that we derived. And these equations are of sufficient number to be solved, taking note that the unknowns p, xo, and yo can be determined and further simplified if your delta angle is either 0 or 90 degrees. Okay, so if your P is vertical, then your delta is 0. If your P is horizontal, then your delta is 90. Okay, so in gravity loadings, it is normal that your P is vertical, therefore the summation of moment can be simply reduced to a value of E, okay, plus XO cosine of 0 is 1 plus YO sine of 0 is 0. So you will be uh, looking into an expression, a remaining expression in terms of E plus RO here in this regard. So here the distance RO is parallel to E or perpendicular to the line of action of P, which defines the distances between IC and CG. So the concept of instantaneous center is identical to the elastic method when the resistance Ri is proportional to the deformation. Stress is proportional to strain, and therefore your uh, delta for both methods of elastic and inelastic behavior, uh, the deformation is proportional to the distance di from the instantaneous center of rotation. So for strength analysis, the two approaches have been used. For the bearing type connection, slip is neglected so that the deformation of each fastener is simply proportional to the distance from the instantaneous center, and an expression proposed by Fisher relating the uh, resistance, which is coming from the elastic behavior, can be expressed in terms of the ultimate resistance coming from the inelastic behavior multiplied by this expression in the parentheses using the Naperian base E uh, and an exponent of negative 10 to the delta, where delta is actually 0.34 inch uh, as given here to represent the maximum displacement at failure. So let us illustrate, for example, the procedure on how to determine the nominal strength Pn that may be applied to the fastener or the fastener group of this figure below. So delta is now equivalent to 0. So use the load deformation relationship given above and assume the maximum deformation to be 0.34 inch and full shank cross section of the bolts resist the shear. So there's no reduction on the threads because this has a full shank. Okay, so the location of bolts 1 to 6 are determined by simple dimensional description here, the centroid of which is exactly at the middle, and the eccentricity from the center of gravity of the vertical load P is given to be 5 inches. So for a 78-inch A325 bolt, we solve for the resistance and using the parameters below. Take note that Fu is simply 120 for an A325 bolt. AB is simply the area of a circle which has a diameter of 7/8. Tau u is zero point 0.7 of Fu. Okay, in this regard, we're not following here the von Mises criterion on the ultimate shear strength. So delta max is 0.34 as given by the works of Fisher. Okay, as far as the exponent delta is concerned, therefore the ultimate resistance of the bolt now is equal to tau UAB, where tau u is simply 70% of your Fu, and Ri is simply equal to R ultimate multiplied by the expression 1 minus e to the negative 10 delta whole expression raised to 0.55. Note that delta is 0 and the sine of the theta angles is equal to yi over di, and the cosine of theta angles will be xi over di. And the following equations are now generated. Since the sine of theta in this case is 0, then your summation Ri, yi, di will be equal to 0. So the cosine of theta is xi over di, therefore the summation of Ri xi over di is equal to a non-zero value equivalent to Pn. And for your moment equation, your summation Ri di must be equal to Pn times E plus Ro. So all of this formula here were simply derived from the basic formula of equilibrium referred to these expressions. Okay, for the deformation distance relationship, it's just like a proportion that the deformation brought about by the load P is actually proportional to their distances from the instantaneous centers. Okay? And therefore, if I have here a delta I over a delta max, then the distance I can also be related to your distance maximum, where delta max is 0.34, so that the above delta I shall be used to solve for Ri then, and the rest of the solution shall be performed by simple iteration. So I did this in MathCAD. So my step 1 in MathCAD simply defines my x and y d values based on figure above. Okay, so I use a counter equivalent to the number of bolts 1 to 6. The trial value, you can set it any number you like. And taking note that at this particular point, we're just making a trial and error solution assuming that RO is equal to 3. Then we come up with these values. For step 2, you make the proportion. So these are my distances, okay, based on the xi's and the yi's. Okay, so take note before I forget that x and y's are reckoned from the instantaneous center, not from the center of gravity. Okay? So if I have here my figure and I assume a value of 3 here, okay, my xi's are simply this is my axis, okay? So my xi's from this origin, if this is 3, will simply be equal to RO 3 minus, okay, this distance from here to here is half this distance. So this is 3 minus 2, 3 minus 2, 3 minus 2, and this is 3 minus uh, this is from here, sorry, from we are reckoning from the centroid, so here to here, so it's now, we will now have here to here, okay? So this is simply reckoned from 3, so this x here is now 3 minus minus 2, okay? So 3 minus minus 2 and 3 minus minus 2 will give you a 3 plus 2 value. So these are now the results, no? 3 minus 2, 3 minus 2, 3 minus 2, and 3 minus minus 2 is simply 3 plus 2, 3 plus 2, 3 plus 2. Of course, if you are using a different value of RO, this will be different. Okay? So for your Y values, you refer now to the centroid again, going, okay, this going upwards and downwards. So this is simply becomes positive 3, 0, negative 3, positive 3, 0, negative 3, which is this one here. So the value of RO does not affect the Y value here, so that your DI can simply be solved using Pythagorean theorem. So solve for the deformation using the deformation distance relationship as implied a while ago. So this is just a ratio proportion automatically upon computing your DIs and getting the maximum of those DIs, multiplying it by the delta max, you get your delta I's. So the resistance of the bolt then, each bolt then can be used using the Fisher equation. Okay, so this is now on the basis of the different values of delta I's computed on step 2. And for step 4, we simply get your RIXI over DI and RIDI to substituted on the two equations. Okay, so the first equation containing summation of forces horizontal equals 0 is just used to check, okay, your final value of Pn. So take note that Pn here and Pn here should converge. And what you are going to do is you simply make use of a trial and error value of your RO until this solution converge, meaning to say both are very very near to each other, or one may be a fixed value while the other is changing. Okay, so the criteria for convergence now will simply be uh, dictated by the values of Pn on both equation approaching equivalent values, such that Pn on the first equation must converge with Pn on the second equation, or Pn on the first equation does not change, okay, while Pn on the second equation changes considerably. So in either of the two cases, convergence is said to be met. So in this particular solution, I think I will show you on the MathCAD file later program, that the value of RO that gives you such convergence to occur is 2.06. So for the slip critical connection, the value Ri shall be taken to a constant value Rs, so that the equation of the equilibrium becomes this. So they are just the same, but of course the only difference is that Ri is no longer uh, a value coming from the elastic, okay, uh, definition or derivation, while Rs is coming from the inelastic value as defined a while ago on our equation for Rs. Okay, so this is our equation for uh, Rs. Okay, so I have not placed the equation there, but you can actually refer to the AISC manual table 7-3 to come up with a value of Rs. So the procedure is just the same. The only difference is that instead of having an Ri, we have an Rs here. So we just plot the data again using MathCAD and make a trial and error solution RO such that convergence will be met. Okay, so the only difference again is that in this particular equation, um, the vector values in consideration of these three equations assumes, okay, that Pn is a function of your Rs. And the convergence criteria here does not manifest or cannot be seen on how near the value of a Pn on this equation for the moment and Pn on this equation for the summation of forces vertical, uh, because there is a misbehavior that can come up since there are values of di equivalent to 0, so this will actually overflow when you use a program. Okay, so a good technique here is to assume a value very near to convergence. Okay, so let's say this is 0.0001 or simply 1.999. Okay, such that if you change the value slightly with this very small increment, and you found out that the value of this is changing while the value of this does not significantly change, okay, then convergence is said to be happening. So in this regard, the final value for your RO that assumes or manifests convergence in this particular uh, solution is very, very near to 2.0. So we can assume that RO equals 2 is the uh, correct value for RO, such that Pn, which is equivalent to 2.857, now represents a factor. Okay, this is the factor that is to be multiplied to your RS. Okay, remember that here there's still an RS. Okay, RS that is present. While in the solution for the first part here, your Ri is actually uh, inside, okay, the summation series. So it's not a constant. And therefore, if we look into that scenario, we can simply solve for Pn by multiplying the value of 2.857 to Rs, and in which Rs comes from the AISC table, happen to have a value of 10.3 kips. Okay, and finally a value of Pn which is equivalent to 29.427 kips is achieved or is obtained as your final nominal capacity. Okay, and that is of course considering a slip critical connection. It is just normal that that value is very much smaller than this value here. The correct value is not yet 143. I think this is something like 138. Okay, if we assume a value of RO equivalent to 2.06. I'll show you the program after this video to give you uh, a more clear and a clearer and a more comprehensive understanding of how the MathCAD program works in this particular problem. Thank you very much, and I'll see you in the next video. Have a nice day.